All right. So the last class, we talked about two different puzzles. The first is when a knight is trying to find a princess. The princess is in one of three caves. In the other two caves, they're dragons that will eat the prince. And so he's trying to find the princess. He can choose any cave he wants. He has a 1/3 chance in this scenario, or a 1/3 probability of making the correct decision. Another way to look at this is that he has a 2/3 chance of making the wrong decision. But what's the probability that he succeeds? 1/3. It's good to note that he fails with a 2/3 probability, but there's not much more to say in this example than that. Sorry, there we go. So we came to this answer very quickly. The probability that he finds the princess is 1/3. And we went through this derivation. I mean, it looks like a mess now. But while we were doing it, the idea is that there's a princess in a cave and dragons. So we talked about what it would look like to have a princess in a cave with dragons, and then we looked at the knight choosing a cave. Each of these are probability spaces, and that's what we defined. A probability space is two things. It's a set and a function that maps points in this set to some number between 0 and 1. You can take these and combine them together. So if I call this 1 and I call this 2, then this is 1 plus 2. I'm mixing the two now. And so this is what we did the last class to actually show that the probability is 1/3 formally using the math of probability, which isn't too bad. I mean, basically, the probability of a success in could be that the princess is in cave 1 at probability 1/3, and the knight chooses that one, cave number 1, with probability 1/3. And so there's a probability of 1/9 that both of those things happened together. That's one way that he could be correct. He could also be correct with a 1/9 probability of the princess being in cave 2 and him guessing correctly cave 2, or that the princess is in cave 3 and he correctly guesses that the princess is in cave 3. All of these ways are ways that the prince can succeed, and when you add them together, you get 1/3. Sometimes students are confused about when to multiply probabilities and when to add probabilities. You get better at it, but in the beginning, if you're confused, think that when you're multiplying probabilities, like we did here, to get these 1/9, we were multiplying This was 1/3 times 1/3. Later, though, we're also adding. So we're multiplying probabilities, and then we're adding probabilities too. So how do you know which one to do? The rule is that pluses correspond to ors, and multiplications correspond to ands. So this 1/9 comes from the fact that the princess is in the first cave, and the prince goes into the first cave. So the princess could be in the first cave with probability 1/3, and the prince with probability 1/3 could find her in that cave. So this is where each of the 1/9ths come from. And we're adding these together because we want to know if the prince can find the princess. And he can find her if he guesses right and she's in the first cave, or he guesses right and she's in the second cave, or he guesses right and she's in the third cave. And those are all of the ways that the prince can find the princess. All right. Let me pause and ask, or give you guys a chance to ask questions about any of this. If you're confused on this, you'll be more confused on when we extend this puzzle. So if you're confused now, ask a question or say which part you're lost on. Nothing. Okay. Then let's go to the second part of this puzzle. So in the first part of the puzzle, let me stop. Let me pick somebody out here. How about Vincent? Do you have a mic?
Yeah.
Hey. So what's the difference between the first puzzle and the second puzzle? Can you say in your own words what the first puzzle is? I can go back up to remind you if you like.
Yeah. I'm just looking at my notes.
Mhm.
Oh, it's the wizard, right? Tells him.
Yeah. So right. So what's the difference between the first and the second puzzle?
Well, in the second one of the caves, I guess, gets eliminated because the wizard tells him.
Yeah, great. Um, of the three caves, like what's the order of events that these things happen? With the knight choosing a cave, with him getting information, and with him having a chance to change his mind. Like when do these things happen?
Well, in the second one, I guess he picks a cave,
Mm-hmm.
and then the wizard tells him um, that there's a dragon in one, like in say like cave two if you picked cave one.
Mm-hmm.
So then after that, he could either stay with cave one or
Mm-hmm.
switch to cave three.
Mm-hmm. Right. Okay. So let's say the knight comes up and he chooses cave two. He's like going into cave two to find the princess. Now he's stopped by the wizard. What would the wizard say to him? So
Well,
the
he would
knight's
tell him
yeah.
that
Go ahead.
there's a dragon in one of them. Um,
And one of which? Which ones?
One of the ones that he didn't pick.
Which are which ones?
I guess in your example, it'd be 1 and 3.
Right. Okay. Very good. Very good. So why doesn't he say cave 2? Or why can't the wizard talk about cave 2?
I'm not really sure.
Okay, yeah, that's fine. Basically, because that's not the problem. Like the problem says that the wizard picks one of the other two. If the
Okay.
wizard could reveal cave 2 as well, that's a different problem, and the things that we're saying now wouldn't necessarily be the same. But you're correct. Okay, great. So yeah, the wizard can only reveal one of two caves. And when the wizard reveals a cave, what's in the cave?
Well, he reveals the cave, and he'll say like there's a dragon, and if like he reveals cave 3.
Yeah, would the wizard reveal the cave with the princess?
Nah.
No, correct. Right. Yeah. So these are the types of things that are important when doing the math kinds of things. So the last class we spent a while going through this. So what um, without the wizard, the prince has a 1/3 chance of being correct. With the wizard, uh, the prince is given a choice of to continue on the cave that he first chose or to change his mind and go to the cave that the wizard did not reveal anything about. So, what should the prince do in this situation?
He should switch
He
his
should
choice.
switch. Okay, great. Thank you. Yeah, thanks a lot, Vincent. I want to catch in with somebody else. Very good. Yeah, yeah. Um, how about Asher?
Yep.
Yeah. So we were told that the prince should change caves. He should change his mind about which cave to enter into.
Right.
Why? Why is that the case?
Because if I remember correctly, he has a 1/3 chance of picking the right cave, but if he changes his mind, that means he's a 2/3
Mhm.
chance of picking the right cave.
Yeah, and so why is that? Why is it 1/3 and 2/3? Like, why isn't it a half and a half?
Uh, I was actually thinking about asking you, even if with the honest, you're asking because the honest wizard says that cave 2.
Mhm.
I was actually just thinking about that. I was confused. I was thinking about asking you about that.
Oh, you mean why it's 1/3 and 2/3,
Right,
not one half, one half?
even if I forget if we covered it the last class, but I kind of forgot.
Okay, great, great. Well, yeah, I'll definitely cover it again. Thanks. How about Mateo?
Hi.
Hey, so what do you remember about this? I mean, why is there a difference between um, when the
I mean,
wizard gives information, or I guess more importantly, why is it not a half a half choice for the night? Why is it a 1/3, 2/3?
I don't remember exactly because we went through like the mathematical stuff.
Yep.
The example that I remember that cleared it up for me was when you broke it down into like 100 caves,
Yes.
that he would reveal all except two, and that like made more sense for me because
Mhm.
it's almost like there's like a 99% chance that it's the cave that he hasn't chose because the wizard revealed all the other caves.
Mhm.
He's not going to reveal the one with the princess.
Yeah.
So it's almost like you had a 1 in 100 chance of choosing initially, and now the wizard revealed all the other caves. So now it's still like you only have like a 1 in 100 chance of sticking with the cave you chose. but now the other cave has a much better chance of having the princess in it.
Perfect. Yeah, that's a very good understanding. Yeah, excellent. All right, thank you very much, Mateo. Yeah. I hope that that made sense to other people. Let me scroll down to this part of what Mateo said had things make more sense to him. This, where if you have many doors, then there's a certain probability when a knight chooses a door to be correct. And after the wizard speaks to the knight's chance of being correct on the first choice that he made doesn't change. But the door that he has a chance to switch to, how to say this? Here, if there's 100 doors, then the knight has a 1 in 100 chance of choosing correctly. Maybe he chooses that door, because whatever. He's correct here. 1 out of 100. Great. Now, the wizard is going to be opening up all of these and showing him that there's dragons inside. But he has to keep one other door. Initially, each of these had a probability of 1 in 100 being right. Whatever, all of these had a probability of 1 in 100 being correct. So when the wizard starts eliminating these possibilities, not this one, what happens to these probabilities? Here, all of these probabilities, where do they go? They all sort of pour into the other remaining door. So after the reveal, here, the prince still has a 1 in 100 chance of being right. But, I'm sorry, actually these go into the other two. They go both places equally. So, in this case, I'm sorry. Yeah. I'm sorry. Yeah, the wizard reveals all dragons minus where the princess is. So this probability hasn't changed, but all of these other probabilities, they like pool up here, and now this is 99 out of 100 that the princess is going to be in that cave. So this is the way that the probabilities kind of move. Once you know that something, when you know that the princess is not here, then you take the probability that the princess was there and update all of the other probabilities, given that you know something about it. If you know something about all of these things, then all of their probabilities get pooled into the other choice. So yeah, I agree. I think that thinking about it, this is actually just in general kind of a good tactic, to take an idea and then try to blow it up into something that's much bigger, or shrink it down into something that's really, really small, to test the extremes. So this is an extreme version of the same puzzle. And in this extreme version, it's easier to see why changing your mind is better. In the version that we talked about with 3 things, the probabilities don't change that much. I mean, you walk into this scenario with a very low probability feeling of success. So having a chance to change your mind makes more sense. But when you're dealing with 3 things, that's harder to have like a gut feeling for, because the difference between 1 out of 100 and 99 out of 100, that difference is a lot bigger and you can kind of feel it. But in this case, the difference between 1/3 and 2/3, it's so close to the difference between a half and a half that people just kind of settle for a half and a half because it's more common, it's easier to think about, it's flipping a coin. I mean, like, that's kind of the most basic model that you could have. And so when it's like a 1/3, 2/3, it's a little weird feeling, like to settle in on that. But in this big example, maybe that has more of an impact on why it makes sense to make a change. And again, that's just like a good tactic in general if you're trying to understand something, to make it really big or to consider extreme cases and what happens then. So the denominator doesn't change when evaluating it, basically. Yeah, sure. Yeah. Yeah, you can consider that the denominator does not change. There's nothing incorrect with that. Okay. So,
Hey, Professor.
yes.
I still am having difficulty trying to understand this because I think of it as, say I was playing devil's advocate and the knight actually chose the one with the princess.
Yeah.
If the wizard just reveals, 98 in this 100 problem, if he reveals 98 randomly, then why would all of the probabilities still go to the door that we didn't choose? Is that just because the wizard is a person and he doesn't want to show you what you want to see? Does that make sense?
Yeah, no, yeah, it does make sense. Yeah, it's a really good question. So the question is basically, the argument is that you should change your mind because things will probably work out better for you if you do. In this case, what that means is that 99 times out of 100, changing your mind is the right thing to do. 1 time out of 100, changing your mind is bad. And this is what this student just brought up. We have, our whatever 100 doors. The princess is in one of them. Along comes the knight, and he picks the door with the princess. He did it correctly. Again, he has a 1 out of 100 chance of doing this. And now comes along the wizard. And the wizard is going to be revealing doors. And the wizard can pick whichever one he wants. The difference here is, let's say, in this case up above, in this case, the wizard is forced to reveal all the caves except the one with the princess inside of it. So the wizard doesn't have a choice in this case. Which caves he's saying has a dragon, he's forced into that decision, because he can't reveal the cave that the knight is going into, and he can't reveal the princess. and there's got to be only one cave left to let the knight be able to change his mind and choose that cave. So in this scenario, when the knight chooses incorrectly, the wizard will do the exact same thing all the time, which is reveal all the caves except the one with the princess in it. In this case, the wizard has a choice. For example, he has to leave one cave open. The wizard could choose this cave, or he could choose that cave. Doesn't matter. He could choose the first cave, or he could choose the second cave, or he could choose the third cave to give the choice to the knight. So in this way, this is why, in this case, you have 99 times out of 100 of being wrong, because with one chance out of 100, you change your mind and choose the first door. With one chance out of 100, you change your mind and you have a chance of choosing the second door. And when you add up all of these ways that which caves could be revealed, all of these, whatever, equal 99 out of 100. So in this case, changing your mind is bad. But that doesn't change the fact that that will only happen 1 out of 100 times. Only one time in 100 can you choose correctly on your first choice. But there's 99 out of 100 ways that changing your mind will get you to the right choice. So it's not guaranteed, it's not a 100% thing, but it is the right choice to make.
Right. And I have trouble wrapping my head around that, but
Mhm.
I appreciate it. I appreciate the explanation.
Sure. Which part are you getting lost on?
No, this actually made me understand it a little bit more, but I don't know, like I'm thinking about it in if there were 3 options in total,
Yeah.
why would one become, or the one that you chose become 1/3, the one become 2/3? But it's because the wizard doesn't want to reveal the princess's door, so he's forced
Yeah.
to show you the opposite one.
Right. Mm-hmm.
Okay,
Yeah.
kind of understand it.
Okay. Let me. Do you understand this idea about the pooling of probabilities in the
Yeah,
case that the knight chooses incorrectly?
I'm sorry.
In the case that the knight chooses incorrectly, so in this
Right.
scenario on the screen, do you understand or kind of why all of these probabilities that were on the cave sort of pool into this one event happening?
Yeah, I can understand that, and that's because the wizard does that by eliminating the 98, right? He all pulls into the other one.
Yeah, because the wizard is telling you. I mean, this on the very end here, this very last cave has a probability originally of 1 in 100 because the princess might be behind it with a probability of 1 in 100. But
Right.
when the wizard says that there's a dragon there, then you know that the princess isn't there. And so this 1 out of 100 probability of this being the right choice doesn't apply anymore. So you now get to move this probability to update all of the other probabilities of other things being correct. And each time he eliminates one of these things as not being where the princess is at, then each of their probabilities of being correct you can apply to other events that could still be the case.
Right.
So if you can understand that concept anyway, then with 3 caves, it's a pretty easy thing. Let's say the princess is here and the knight chooses this cave. He has a 1/3 a 1/3 probability of being correct. Each of these have a 1/3 probability of being correct. But then along comes the wizard, and when he reveals a cave, he has to reveal this cave. Only this one. Because he's got to reveal a dragon. And therefore, this probability gets moved over to the other choice. So that's where the 2/3 comes from. The 1/3 never changes. The 1/3 is always 1/3. The first
Now, is it
choice always
because he
has the same
chose that
probability.
when there were 3 options available? Is that because he chose it with 3 options available? Like, what?
Yeah.
Like, I know I keep making you explain the same thing, but it's like, why
fine.
wouldn't a little bit of that 1/3 go to what he already chose? Is that because he chose it when there were 3 options available?
It's because he chose it when there were 3 options available. Yeah. And the wizard revealing, in this case, cave 3, doesn't affect the probability of the cave that he's going into. I mean, so this is why, I mean, I'm trying to give intuitive ways of understanding this, because it's a really interesting concept. I mean, it's something that a lot of people get wrong, and it's nice to know why that happens. But this is one way where the math can kind of make it easier. You can just calculate it. And so here, this is saying that the probability of the knight choosing correctly the first time, that's B1, is independent of which cave the wizard reveals. When I say it's independent, I mean that if the wizard reveals this, then it doesn't change this probability. It doesn't change the probability of your first choice. That's what it means to be independent. And you can show that it's independent in this way. I mean, like that the probability of this occurring with this, they don't equal each other. They just don't fit the definition of independence. There's a number of ways actually you can argue this, but the thing that's a little hard to convey is why this cave, whatever the first choice is, the first choice is independent of the wizard. The best way I can think about trying to explain it without math is saying that in this case, the wizard is forced into revealing certain doors. And in this case, depending on what the knight does, this can change the way that the wizard responds. It can force the wizard to do something, or in the rare case that the knight chooses correctly, then the wizard has a bunch of choices as far as which cave he wants to leave unrevealed. And so these other caves are dependent on the wizard. They're dependent on the wizard and the choice that the knight makes. But the choice that the knight makes first is independent of what the wizard says. Maybe another way of thinking about it is that the knight made a choice before he even knew about the existence of the wizard. So the knight's choice was made without knowing anything about what the wizard said. And so once the wizard tells him something, it doesn't change his original choice, like that probability. It can only change the probability of choices he didn't make.
Okay.
Okay. Yeah. This is it's a very good problem. Thank you, Sean. I know that it's hard to wrap your head around. That's part of the reason why it's a famous problem and stuff. Yeah, it's one of these things that you can think about for a while and still not necessarily feel super comfortable with. As far as this class is concerned, the reason why I'm introducing this is, one, because it's a very, very good example of applying conditional probabilities, independence, probability spaces. It's a really good exercise for that. But also, it's a very good life lesson. I mean, that in even some simple cases, like your thoughts about how likely something is can be wrong, like in ways that require explanation and thought, even in some simple cases. So, yeah, it's important to be careful or to trust people who might know better, or to press people who just say some numbers for how are they getting those numbers, even if you don't understand where they're coming from. Like, can they explain them? Yeah, you guys are in business school, so I'm assuming that this is the kind of thing that you'll be dealing with a lot in your later careers. So yeah, hopefully that's something that I don't know, benefits your later lives. Okay, so I won't talk more about this problem. It's been long enough of a review, I think. I will say that spend some time on it and try to feel comfortable with this. More importantly, understand how to build probability spaces. Let me find one. Really? There's got to be a probability space here. This is a probability space. A set of events and their probability of happening. That is a probability space. Be comfortable figuring out how to build those. And also what conditional probability is. When you update probabilities because you know stuff. Okay, so today we have to move on to new and better things. I won't be talking about probability by itself. I'll only be talking about what's sort of an extension of probability. It's like, I don't know, probability with armor or something. Like, I don't know, it's an upgrade. Probability is the philosophy, there's math behind it, whatever, about what could happen and the probability of any of the things that could happen actually happening. That's it. That's everything that probability talks about. Events and the probability of these events happening. You need both. It's important to know, I've said it 100 times, I'll keep repeating it. A probability, when you're talking about probability, you're talking about two things. Events, written here as omega, and here I'm writing a function as the probability that is the probability of any of these events happening. You need both to work with. Once you have them, you can calculate stuff, but you need to have them in the beginning. Otherwise, you're not doing anything. I mean, it's not probability. Okay. So probability you can do a bunch of stuff with. You can try to make predictions about how likely certain events are to happen. But there's another really useful thing in math, which is numbers. Can you take numbers as in, 1, 2, 3, 10, 100, 1,000, can I take numbers and kind of attach it to probability? So I'll take the events and I want to assign numbers to these events. And that way, when an event happens, a certain number appears, and I care about that for some reasons. This is called random variables. Random variables are an extension to probability, where you assign numbers to events. So, this is useful for computing averages, something called variance. That's how much things are different than the average. You can calculate all of these things if you have numbers to work with. If you tell me that the probability of rain today or not, that's fine. That's something that can happen or not. But there's no numbers with that. Can I talk about an average? No, you just talked about whether it's going to rain or not. There's no number attached to it. But with numbers, you could calculate average incomes, you could talk about the number of days it rains this year, things. These random variables are also called probability distributions. I happen to like probability distribution better. I'll use both, but I think that a distribution is a better way to think about this instead of a so-called random variable. I'll talk about both, and I'll justify these things as we go on. Let's see. Okay, I'll take the next few minutes before break to show you this awesome drawing that I made. I don't want to show all that, just the drawing. Yeah, look at that. Prepared for this class. Anyway, okay. So, this drawing is something that I want to illustrate. No pun intended. This is an object, a cube, and this cube has colors. And so what I'm trying to show in this diagram is what the cube looks like. I mean, I can't show you in 3D a cube. So here I drew a cube, and these colors along the edges here are the sides, or the color of the sides that you can't see. So here, the sort of pinkish color is the bottom of this view of the cube. On the left would be this sort of light bluish view of the cube. And so here, if you take the cube and you rotate it 90 degrees to the right, then the yellow face will move to the right, the orange stays where it is, and then the blue moves to the front. And likewise, having the color green face you, or looking at the bottom of the cube, if you kind of pick up the cube and then move it backwards, turning it 90 degrees along a different axis to view the bottom from this, this would be the view. In any case, it's a cube with 6 colors. And let's assume that this is a fair cube. Okay, so I'll describe the result of the cube as whichever color is on top of the cube. Okay, that's how I'll describe the result of the cube. So here on the left, the result of the cube, I'll call that orange, because orange is on top of the cube. These are also orange results, even though other parts about the cube have changed. Orange is on top, so I'm going to count that as an orange cube. Or as, I don't know, the result being orange. And here on top, this is a result of yellow. Okay, so just colors. It's a cube. The cube has 6 faces. Each of the faces have colors, and it's a fair cube. So you throw the cube, any color could appear on top with equal probability. That's 1/6. And when you roll the cube, you say that the result of the roll is whatever color appears on top. That's it. Okay, before I get into the next part, I think maybe we can take a break. So let's come back at like 3:10. That's around a 10-minute break, and we'll continue. Great. So, this class we're talking about an extension of probability called probability distributions or random variables. And to emphasize the difference, I want you to get out of your head numbers and probability. So here we're looking at a cube with colors. Let me pick, how about Brian? Do you have a mic?
Hello.
Hey. So to describe this cube, let's say it's a fair cube, what would the probability space look like?
Well, it would be, like you were saying, orange would be one.
Okay.
And then like purple, pink, yellow, blue, green.
Blue, whatever, green. Okay.
And then like, the probability of orange would be equal to the probability of blue, would be equal to the probability of pink and yellow and all of them, which would be 1/6.
Excellent. Okay. So this 1/6 is a number, but that has to deal with the probability function. This set of outcomes, there's no numbers, right?
Right.
Could you talk about the average of this cube? Is that something that would make sense to talk about?
Like the average outcome? Or that in I'm not really sure what the average of the cube would be.
Exactly. Very good. That's right. It's a question that doesn't make sense.
Okay.
Yeah. Yeah, there is no, I mean, yeah, what the
Okay.
average what? There's
Yeah,
colors.
right.
There's no average to talk about. I could talk about a color that it could be and a probability of that color, but that's it. That's as much as exists in this scenario. Very good. All right. Thank you very much, Brian.
Yeah.
So that is sort of the point, that you can describe events, or that probability just describes events and their probability of happening. This was exactly right, this probability space, but just because I had time before class, I made it pretty. So this is the probability space. It's exactly what Brian said, just whatever, I used colors instead of writing out the spelling for the colors. So that's a probability space. Now, a random variable turns events into numbers. So let me start here. A random variable, when I say maps, what I mean is that it makes one thing into another. That's what maps means. And here it maps outcomes, so these are colors, to real numbers. And I'm writing this letter here, this R, with this 2 kind of strokes on the left-hand side. That's just a common thing to do in math, to refer to the set of real numbers. Real numbers are numbers that I tried to give some examples of down here. So basically any number you can say, or any number that you would see in nature. So that includes negative numbers, it includes fractions, it includes numbers like pi, that are numbers that written as a decimal go on forever and ever and ever and ever. Real numbers is the set of all of those types of numbers. Real numbers do not include things like I, which is equal to the square root of -1. Real numbers do not have this, or rather, it's written this way. This does not exist in the set of real numbers. Whatever. These are called complex numbers, but we don't need to talk about this stuff. Just know that real numbers are just any number that you can think of, basically. The normal numbers, including fractions, positives, negatives, anything. So a random variable or a probability distribution will map these outcomes, and outcomes don't have to be numbers, but the result is a number. So I could assign numbers to each of these colors. Maybe I want to make it more like a regular die. And so I'm saying, okay, well, if a yellow one comes up, I'll call that a 1. If I see a green, I'll call that a 2. Or if I see a purple, I'll call that a 6. And the other things in between. So this here on the left is a random variable or a probability distribution, and this is defined building off of a probability space. So this is what I mean when I say that a random variable is like a probability space with an upgrade. You have the probability space, the entire thing, but in addition to that, you have a mapping of events to numbers. This is another sort of graphical way of thinking about it. Here you have some set of possible events, a set of possible outcomes. Here this set is of size 6, and each of these points you can think about it however you want. Maybe these are colors, maybe they're smiley faces, maybe they're anything you want. But for each one of them, you put it somewhere on what's called the real number line. And this is basically a line that extends to infinity, negative infinity to infinity. And so for any event, you assign it a number. You can think about it like this, you're just giving it a number, or you can think about it like there's this infinitely long line, and points from the set are mapped to somewhere on the line. Here, I'm highlighting this in blue because that's what I mean to map. And in addition to mapping the value, each of these numbers has a probability of happening. And the probability of these numbers is equal to the probability of whatever event is mapping to it. So in this case, the probability of 1 is 1/6. The probability of 2 is 1/6. The probability of 6 is 1/6. Everything is a probability 1/6. Why is the probability of 1 1/6? Well, if you go back along this arrow and you look at this event has a probability 1/6. So this also has a probability of 1/6. Okay? All right, so that is how to understand what a random variable actually is, as well as a probability distribution. These are the same things. The reason why I like a probability distribution is, let me draw this a different way. This is another way to view this, sort of pictorially. That's a common way of doing it. Here we have a probability, 0, 1/6, 2/6, whatever. And then here you have numbers. So here we would have 1, 2, 3, 4, 5, and 6. So along the x-axis, we are putting whatever numbers that things map to are. And along the y-axis is the probability of this happening. So here, another way to look at this is like this. I'm sorry, hang on just a moment. Give me a couple of minutes. I apologize. So this is another way of looking at a random variable. And the reason why I like the probability distribution wording better, because I think that this is a good way to, in your head, think about what a random variable is it's a distribution. In the same way, you can't talk about this cube. I mean, is this cube yellow? It's not yellow. It's a bunch of different colors. If you talk about the outcome, what's going to be on top, I can't say that it's yellow or purple or green. I can talk about the probability that it's yellow. I can talk about the probability that it's purple or the probability that it's green, but I can't, this cube is no one color. I mean, what we're talking about is a probability space. And so there's things that could happen and their probability of happening, but that's as much as you can say. So similarly here, a random variable, the reason why it's called a random variable, the variable is a number. It's going to be some number. That's what the variable part of it is. The random part is because it's not one number. It can be a number. Here, if I roll the die and I see a yellow, then I can say that I have a 1. But the random variable isn't 1. It has a probability of being 1. It has a probability of 1/6 of being 1. So these are important distinctions and ways that people get confused, which is why I'm emphasizing it so much. You can't say that a die is the number 4. You can only talk about the probability of a die being 4. Okay, so with that, let me write a formal definition for a random variable. Okay, so this is the way to write it shorthand. It's a function. I'm calling the function x, and the function is defined, that's what the colon is, as a function that maps a set to real numbers. Okay, so that's the arrow here is the map part. For the visual, this is what I mean when I say mapping. So the random variable, this thing is a function, and it takes outcomes and gives them numbers. Okay. Right. So one of the really important things about why people care about this idea of a random variable is because you can do math with numbers. You can do different kinds of math. So here, let me call this variable, or this function, I'll call this x. Okay. So, well, I don't want to make it. I'll call this function x. So this is a function, this is a random variable, this is a probability distribution. All of the same things. So I could ask questions like, what is the average value of x? Let me put this, the value of colored cube. As I think Brian said before, the answer is can't answer. There's no numbers. Average color? What does that mean? Average shape? I don't know, whatever. You can't answer it. But if I ask, what's the average value of x? This is something that we can talk about. This is something that is clear. Here, I'm going to write it this way. Sorry. The average or mean value. Oh. Technically, it's still the probability space. I'll leave this out for now. The expected value of x, this is a definition, is defined as being 1. 1 can happen with probability 1/6. So the way I'm calculating this is for this outcome, it has a probability of 1/6 happening. Or another thing that could happen is that I could see a 2, and that also happens with probability 1/6. Or a 3 with a probability of 1/6, or 4 with a probability of 1/6, 5, or 6, probability 1/6. Okay, let me pause here and ask somebody what this equals. How about Jelani? Do you have a mic?
Yep.
Hey.
Actually,
Or you might know it off the top of your head. Like, what's the expected value of a die if you roll it?
the expected value of the
How's that?
die. Could you rephrase that a little bit?
Oh, could I write it a little bit? No, you can. Oh, we can calculate it. I mean, just can you calculate this?
Oh yeah, it's 1, but like it would add up to 1, but the value of all the individual.
You think this adds up to 1?
Are you individually multiplying each odd? So it'd be like 2, 6, 3, 6.
Yes.
Oh, okay. Yeah, in that case, it'd be 21, 6. 21, 6.
Is how much?
21, 6.
21/6.
Or 3, 3, 6. 3.5. Basically.
Yep. 3.5. Great. Thank you very much. Yeah, very good. Yeah. So this is how you calculate an expectation. I'll give, this is actually an example. The definition of E of x is the sum of x times the probability that x equals x. For x in x. That's the definition. Okay, what all that this means is you take each outcome, that's this little x. Make sure this is a big X. So I'll try to write big X's in this way and little x's with a curve. So I try to do that so you can differentiate them. Yeah, if you don't see a curve, I'm trying to talk about a big X. Okay, fine. So there's 2 x's here, but one is not the same. This is a little x, and that's a big X. So the big X is the set of outcomes of the random variable. And you take the outcome of the random variable, this is going to be a number, and you multiply it by the probability that the random variable could equal that number. Here, the random variable could equal 1, and it equals 1 with a probability of 1/6. Or it could equal 2 with a probability of 1/6, and on and on. So here, the little x's are 1, 2, 3, 4, 5, and 6. And then the probabilities are the same in this case, 1/6 for each of them. And then you add them all up and you get a number. And that is called the expectation. One way you can think about this as a probability distribution is if each of these were weights, like I have blocks that I'm putting on this line, on this line, the line of real numbers, then where could I hold it to make it not fall over? Here, this is the middle point, 3.5 is the balance point. So there's, if you were to actually lay like bricks on each of these places, if you held the middle of what's holding up the bricks at position 3.5, then it would be steady. The amount of weight on the left and the amount of weight on the right are the same. If you move left or right from that, then it's going to get unbalanced and the bricks are all going to fall down. So this is the same as what the expectation is in all cases. If that's another, you could draw a picture and just find the point where the mass is equal on the left-hand side and the right-hand side, and you could sort of eyeball it to see where the balance point is. But this is a way to calculate it. These are the positions of the bricks, and then this is how much mass the brick has. And right, so another thing to notice about a random variable or a probability distribution is that the expected value does not have to be an outcome of the expected of the random variable. So here, the random variable, it can be the number 1 or the number 2 or the number 3, the number 4, the number 5, or the number 6. The random variable, if you roll this die, one of those 6 numbers will show up on top. 3.5 is not a number that you can see. So it's a little strange to say that it's the average, because it's not, you never see 3.5. You see 1 or 2 or 3 or 4 or 5 or 6. So it's sort of an unfortunate use of English to call this an expected value, because you will never see it necessarily. But what it means is that if you were, this is the frequentist point of view, if you were to roll a die 10 times and you add up the number that you got on the first time and the number that you got on the second time and the number you got on the third time and the fourth time, fifth time, sixth time, and you do it 10 times and then you divide by 10, that number would be close to 3.5. So it's the sum of the outcomes divided by the number of times you tried. And if you do it 10 times, very likely, if you add it up and divide by 10, it will be close to 3.5. If you do it 100 times or 1,000 times, it will be even closer to the number 3.5. Maybe you get the number 4 after 10 times, but after 1,000 times, you get 3.505. Something that's much closer. So if you do this many, 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 many times and then take the average of the number that you see, that's what the expected value is. All right. Again, notation-wise, I don't know what your guys' backgrounds are. Let me just ask really quickly. Should I take 30 seconds and talk about this symbol that I just highlighted in blue? Or have you seen it before? You know what it is. Silence. Thank you. Thank you for responding. Yeah. So this thing, notation. This, because people in math love Greek symbols, this is a letter of the Greek alphabet. It's the letter S, and it's pronounced sigma. Pronounced sigma. It's a capital sigma. This is a lowercase sigma. Looks like a 6, whatever. And this means addition or sum. It means a sum. That's why they chose the letter sigma, because they both are the letter S. Together, let me redo this a bit. Okay. Taken together, means the sum for all little x in big X, i.e. x equals 1, sorry, x equals 2, x equals 3, all the way up to x equals 6. So x, the big letter x, these are all of the possible number values. And so, if I didn't say so, notation. Oh. This sort of weird looking E thing, this means element X in set X. So this here, when I write these symbols, this means that this is a set of things and that this is one element of the set. So taken together, this means for each element of the set X, plug in that value here, and for each one of them, calculate this value and then add them up. So let me just do this explicitly. So x can equal 1. 1 in x. 2 is also in x. 3 is in x. 4 is in x. 5 is in x. And 6 is in x. So when x equals 1, then this is 1 times the probability x equals 1 plus 2 times the probability x is 2 plus 3 times the probability x is 3 And you do this for all of them, including 6 times the probability that x is equal to 6. So the probability that x equals 1, that's 1/6. The probability that x equals 2 is also 1/6. Sorry, I'm adding these. All the way until 6 times the probability that 6 is this, which, as we've already said, is 3.5. Okay, is that clear what this symbol means now if you see this? Because this is in your homework, this sort of notation. I hope I've explained it, but if not, ask or unmute yourself. Okay, Asher, do you have a mic?
Yep.
Yeah. So, does this make sense now?
Yeah,
Or-
I knew what sigma was. I just didn't know the XEX under it was, or X sub X.
Got you. Okay, does it make sense now?
Yeah.
Great. All right, thank you.
Thank you.
All right, then... let's see. Right. So I'll say it again. The expectation doesn't have to be a value that the random variable can take. So in that sense, there's not really kind of a real world meaning to it, but it's a very useful concept. Let me come up with some other examples of random variables, or I'll have you guys give me examples of random variables. How about Olga? Are you there? Do you have a mic? Okay, how about Royston?
Yep.
Hey.
Hello.
Yeah.
Yep.
So let's say if we take the example of the knight and the princess.
Yeah.
The original one, where the knight just chooses randomly. And let's say that in addition to getting the princess has a very large diamond ring that's worth $1 million, and they can sell it and buy a big castle. How could we take that and put it into like a random variable? So we have a set. The original one is princess, dragon, dragon. This is a set. And the knight chooses the first cave. And we have a bunch of these. It could be dragon, dragon, princess. And the knight chooses the third cave. How many different events are there here? Do you remember?
Was it 9?
9. Yeah.
Was it 9 total?
Yep. 9. Yep. All right, and then these also have some probability of happening. Just to save time. And what's the probability of any of them happening?
I guess a 1 in 9 chance.
All right, great. Okay, so this is a probability space, right? And what I want to do is take this probability space and use it to define a random variable or a probability distribution. And the number that I'm assigning is $1 million if the prince chooses correctly. So what does this random variable look like?
I'm not really sure what you're asking.
How would you define a random variable? What is a random variable?
A random variable is something we use to assign value to an event, right?
Yeah. Mm-hmm.
Like a number we use.
Yeah. Let's see. So there's 9 events here. Let's go ahead and write them out, actually. I'll give you the first one, and then after that you can just tell me what to write. So we have the princess is actually in the first cave, and the knight chooses correctly. What's another event that could happen?
The same order, but he chooses the second cave.
Yep.
The same order, and then the third cave.
Yep.
And then I guess reorder them and then do one, like the same thing.
Okay, reorder
So it
them
would be
how?
dragon, princess, dragon, princess, dragon. Like do that 3 times and then write 1, 2, 3.
Yep. Okay. Great. Yeah. I said I'll write them out. Let me just write them out. Okay. As I'm doing this, you say that a random variable maps events to numbers. So these are the events. What are the numbers?
Right. I guess we could number them like 1 through 9.
Oh, but this is in the case when the princess has $1 million ring, so he gets a prize. That's what this number is representing. It's the money prize. It's how much they have to spend on their castle.
Okay.
So I'll call that X. Let me move these things down. Okay. Say the princess has a $1 million ring. X. Let X be the money the prince has after his cave choice. Okay, so X is the amount of... sorry, it's a bit sexist, I suppose, but assuming that the princess who's wearing the ring, she gives the ring to the prince, and so this money is now his to buy them to a castle together. So that's what X is. So this is a function that takes in an event and outputs a number. So what would the numbers be for this? Take the first one. Princess, Dragon, Dragon, first cave. Does the prince choose correctly?
Yeah, he chose correctly, so he would.
Okay. So how much money does he have?
He would have $1 million.
$1 million. All right. Okay. How about in the second case, this one?
He would have the same money he came with. He got $0.
0. Good. All right. How about the third one?
0 as well.
Okay. And the fourth?
0.
Mhm.
0, and then he'd have $1 million in the next one.
Mm-hmm.
0 again.
Mm-hmm.
And then 0, 0, and then $1 million.
Great. 1 million. All right. So this is now a random variable. But there's something else that I guess I'm not saying. Along with each of these, there's also a probability. So the probability of this is equal to 1/9. The probability of that is also equal to 1/9. And each of them all have a probability equal to 1/9. So a random variable, don't forget, it's a set of numbers, but it's built from a probability space. So the numbers you can kind of assign it any way you want, but the probability of getting a particular number is equal to the probability of that event in the original probability space. So far, so good?
Yep.
Okay, great. Does this idea make sense as far as what a random variable would be?
Sort of. I guess transitioning from the colors to this is just like it's easy to understand with the colors because
Mhm.
you'll use the number 1 to represent yellow, and then so on and so forth to like number 6. But in this case, it's I'm not sure what I should be assigning the number to. So I see that there's 9 different events.
Yeah.
And I could order them, like I could number them 1 through 9.
Mhm.
Yeah, but it just seems like, I don't know, it just seems a little different. I think I don't understand.
Excellent. Great. Yeah, that's a really good question. So, well, two things. One, there's no order to the events. You can order them if you want, but it's unnecessary and it wouldn't mean anything. If you call this the first event, the second event, the third event, like it doesn't give you anything else. I mean, I could in this set of outcomes, like would it matter if I took this one and I put it here at the end and I took this one and I put it at the beginning? Yeah, it's the same set of outcomes. So order in sets doesn't matter. You can order them, fine, but it doesn't change anything. So with the colors, the reason why I started with this example is because I wanted to try to make the transition easier. That in this set, these are just events. They're not numbers. They can be any event that you want. In this case, the events are just colors. So this is yellow is one event that could happen. When the event yellow happens, I'm defining that as being yellow being on top of the cube. if green, if this event happens, I'm defining that as being green on the top of the cube. And so I can define events in this way, using colors, no numbers. Here, it's the same thing. This is an event that can happen. So for each event in this space, in this set, each one of these, you're going to assign it a number. And it's not an ordering number. You can assign it any number you like.
Yeah.
Here, the numbers that we're choosing to assign them is because we're trying to imagine this kind of scenario of earning money when you make the right choice, or when you make particular choices. Does that clear it up a little bit, or is it still strange?
Yeah, I mean, I don't think I didn't mean order them, but I meant like number them. Like, so the first event we would call it number one, not for the case for the idea of like ordering it, but just calling it number one.
Sure. That's fine if you're like talking to somebody else and you're just trying to not confuse each other. But that's the only use of ordering things like that. Okay. Yeah. As far as creating this random variable, do you have any other questions about it? Like, you start with the probability space and then you assign numbers to outcomes.
No, I guess nope. I think I understand it.
Okay, great. Thanks, Royston. How about Andrew? Do you have a mic? All right. How about, I don't know who I haven't called on. Mateo? I know I've called on you, but whatever. Hey.
Yep.
Right.
I'll
So I want to take this example, and I want to talk about the expectation of it. So we have a random variable, and one of the cool things you can do with a random variable is to find out its expected value.
Okay.
So here, what would the expected value for this random variable mean? Like, can you put it in English words?
Like how much money on average you would expect to have.
Yeah, right. Exactly. Right. So if there were a bunch of, if this was a game that you could play on I don't know, on an Xbox or something, and you choose a cave, and you play the game 1,000 times, how much would you expect to have taking the risk of playing the game? So for that, then, what could you expect for this? What is the expected value?
I think it's $333,333.33.
Yeah. I'll call it 3 million over 9. Oh, actually, no, it should be. Right? Uh, 3 nines. Yeah, right, okay. So this is 1 million, right? How did you get the number that you did? How'd you get that?
Well, wouldn't 3 over 9 be like 1/3? So it would be 1/3 of a million.
Oh, yes, right. Thank you. I just myself had a brain fart. Okay, so 3 million over 9. Okay, I'll write it like this: 3 million over 9.
Okay.
Great. Yes, you're right. So this is 1/3 of a million. Okay. Perfect. Thank you. Okay. So it's already past 4. How about we take like a 10-minute break, and after this, I will introduce to you another concept called variance. and we'll go from there. So let's come back at, I'll say 4:21. That's 10 minutes. Okay, welcome back, everybody. So we're going to continue our talk about probability distributions or random variables. Again, they're a way that you take events that can happen, any event, and I mean, really, any probability space. So this is defined by a set of events in a probability function, and assigning to each event a number. And it can really be any number you want so long it's a real number. There's certain times when it makes sense to use certain numbers. Like in this example, we assigned certain events the number 1 million, other events the number 0, and we chose those numbers for those events because that captures this idea of a knight getting money for making the right choice, in addition to the princess. When you do this and you assign events to numbers, then you can imagine it's called sampling. You take the probability distribution, and at random, according to the probability, some event happens, and therefore whatever number that you assigned to that event happens with the same probability. So that's what's here in blue. Each of these probabilities are coming from the probability distribution. So the probability of getting this 1 million, not 1 million in general, but this 1 million, has a probability of 1/9, and so on and so forth. You can compute the average value, which is a very important, useful thing. There's another notion of average called variance. Variance. This is the average, this is a little weird, squared distance. Not just the average distance, but the average squared distance of around the expectation E x. Formally, the variance of x is, so when you see this E, think average. You can always replace in your head that this E means an average or the mean. So that's this average. The squared distance is x minus e to the x squared. That's this part. Actually, around the expectation is that inside part. So the distance is just subtracting one from the other. That's the distance. It's a square distance because you're squaring it. And it's the distance around the expectation because you're taking the random variable and comparing it to its expected value. So the reason why variance matters, well, we talked about variance a little bit already. With linear regression, this is two possible lines. Let's say the line is e of x. This on the left is high variance, and this is low variance. Okay, so if you want sort of a picture in your mind, even though these have the same average value, the distance, the average distance of these points from the average value is big on the left-hand side here. On the right-hand side, each of the points are pretty close to the expected value. So there's a low variance. This variance, this is actually going to be a number. A random variable is not a number. A random variable can be a number with a certain probability. So random variables aren't numbers. Expectations are numbers. Variances are also numbers. So whenever you see the expected value of something, think that it's going to be equal to some number. The same thing with the variance. Let's continue with our die example and figure out what the variance of the die is. And we'll just use this equation. That's it. So let's see. How about Asher? Do you have a mic?
Hi.
Hey. So I want to try to compute the variance of not this example, where we have the die. So here, example. Excuse me. A 6-sided cube. X equals 1. I can actually define the whole thing in this way. So here we have both the outcomes and the probabilities are all equal probable. Okay. So again, here we have the outcomes and the numbers that they're assigned to. And this line is also defining the probabilities for each of them. We know, recall, that the expectation of x is 3.5. So we're just going to compute the variance of this random variable. I'll start off with the definition. Great. So what should I write?
You mean like just write it out?
Mm-hmm.
So it'd be 1 minus 3.5 squared plus 2 minus 3.5 squared, and etc.
Yeah. Oh, wait. Sorry. 1 minus 3.5 squared, and then what?
Plus 2 minus 3.5 squared. And so on until you get to 6. Yeah.
So what we've written so far is this inside part.
Right.
Okay. How about this outside part?
That's the sum of it. Right? Is that a sigma?
Oh. So you're missing something. What's the definition of e to the x? You remember?
I'm not sure.
Okay, I'm writing it here. In green to the right. So you're right, it's a sum of values, but you're missing this part, the probability.
Okay.
So what's the probability of this?
1/6.
1/6. Okay. Why is it 1/6?
Because there's 6 choices, 6 outputs.
Yeah, it's because that's the probability that x equals 1.
Right.
Yeah.
So wait, where are you sticking the 1/6 into that formula? Like, is it 1 minus 3.5 squared times 1/6?
Yes. Mm-hmm.
Okay.
Yeah.
Oh, okay.
Right.
Yeah, I just had an exam on variance yesterday in another class.
Okay. Great. How'd that go?
It was good. Just use Excel. I'm a big Excel person.
Okay. Cool. Anything you can say about variance? Like, I don't know, something you find interesting or something I haven't said so far, or?
No, not really.
Okay. Fair enough. So this is basically plugging and chugging. So this expectation results in each of these 1/6. Here's the probability of x equals 2. Okay. And so because it can be a little confusing when you start using more symbols and you kind of combine these things, remember, expectation, this is going to be some number. And this part in blue, that's another random variable. It's just a random variable where you're subtracting 3.5 from it. So I could call this x prime. And I could say that this is the expectation of x prime, where x prime equals x minus the expectation of x squared. Right, I can just replace it by another variable. And x prime can be equal to minus 0.25 for 6. And the probability of that is 1/6. Right? So in any case, inside of here, this is still just a random variable, and so you can ask about this random variable's expectation. This is coming from this. And x prime can also equal, just write this, or 2. And so on. Okay. So you do all of this, and this will be about 2.91. Okay. So, this is convenient. So Asher, you say that you've taken, or you just have been recently thinking about variance. So if the expected value for the die, if the expected value of x is 3.5, and the variance of x is about 2.91, and x equals 1, x equals 2, whatever, x can equal 1 or 2 or up to 6. Can you tell anything about what the variance is saying about the random variable? Like, so there's random variables, or there's probability distributions. The expectation tells you what the average value is. The variance tells you the average squared distance away from the average. So what does a big variance mean? Or what would a small variance mean?
I'm not sure, but I feel like in this situation, since the variance is close to 3, and the expected value is 3.5, it covers both sides, so all of the faces are possible.
Very good. Very good. Can you say something more about that?
Yeah, so since the expected value plus and minus the variance is within the limits, all faces are possible. Since it goes to like 0.6 all the way to like 6 point something.
Yeah, very good. Yeah, so for this example, is the variance of 2.91, is that a big variance or a small variance?
Yeah, it's I'll say it's a small variance.
Why small?
Just because I don't know, I got tripped up on that one.
Okay, so here we have the expectation of x, and so this is 3.5. Sorry, let me erase those. Here's 3.5. Right, that's e of x. And the variance is how much things on average are away from this. Let's see. Yeah, so the variance, it's a squared distance. So sometimes, or oftentimes, people will care about the standard deviation. And this is equal to the square root of the variance. The reason why is because here, if the variance is 2.91, then this would be 3.5 plus 2.91. And here would be 3.5 minus 2.91. So this value here is what? About 8.4. And this is I don't know, 0.4, 0.6. But this 0.6 doesn't really mean much because it's in squared units. So instead, if you take the square root of this, I don't know, I'll call it about 1.3. Standard deviation is about 1.3.
Professor,
Yep.
wouldn't the top number be 6.4 instead of 8.4?
Oh, yeah, sorry. Thank you. Correct. Thanks. Yeah. So in any case, this is sort of a more useful region, which is why people care about the standard deviation, because things are in the same units. What this is saying is that you could get 3.5 on average if you do it a bunch of times, but also at times you could get something closer to 4.8. So that covers close to 4 or 5. Here, you could get 2.2, and so that's close to it. It includes 3. It's close to 2, and 1 is sort of on the outside here. So, there's a difference. These two random variables are random variables that I could make from the same die. Here, each of the 6 faces are equally likely. Here, only 2 faces, let's say, give a payout, I guess. So each of these, what's the expected value for the one on the left? Asher.
3.5.
Yep. How about the one on the right?
Would it also be 3.5?
Yeah, exactly. What was x prime? Yes. So here, the variance, this is a high variance for this random variable. The reason why it's a high variance for this random variable is because of this region in green. It covers almost 4 different sides of the die. So while on average you'll get 3.5, as you say, all the faces are kind of possible. So it's very spread out where these numbers are with respect to the average value. Here, these two values are more concentrated. So they have a higher probability as well. In fact, maybe I should draw this a little different. These have a much higher probability of happening. 1/2. There's 1/6. 36th. Okay, so those are closer to scale. So here, the variance is low on the right. On the left, the variance is high. And you can tell that numerically without looking at a graph by looking at this number, the variance. You can actually define a number for it. Okay? Asher, does that make sense, or do you have any questions about any of that?
I think I got it.
Okay, great. Thanks. Okay. Andrew, I see that you're... Oh, you say big. That's a big variance. Yes. Yeah, here it's considered a big variance for the reasons that I said. Okay. One very useful property of expectation is that by definition it's a linear operator, and I'll explain what this means. Definition. This is also called the linearity of expectation. Given random variables x and y over the same space omega and some number c, where c is some real number, one, the expectation of c of x is equal to c times the expectation of x. And the expectation of two random variables, x plus y, is equal to the expectation of the first random variable plus the expectation of the second random variable. So this is a really, really useful property because you can have you can scale a random variable however you want. That's what the C is. So I could take, maybe the number is 10. Let's make C equal 10. Then in the die example, I'm going to be multiplying everything by 10. So instead of getting a 1, 2, 3, 4, 5, or 6, I'm going to get a 10, 20, 30, 40, 50, or 60. And the expectation is 35. It's the expectation 3.5 times the number 10. You can prove these things. I mean, 10 times 1/6 plus 20 times 1/6 plus 30 times 1/6, all the way up to 6 or 60 times 1/6. You calculate it and you'll get the number 35. So that's a useful thing to know. You can scale the when you scale a random variable, then the expected value of the non-scaled random value is scaled by the same factor, which is what the right-hand side says. Whatever the expected value is of the thing before scaling, you can scale that by the same number. And that's the same as scaling it first and then calculating the expectation. So you can calculate the expectation and then scale on the right, or you can first scale and then calculate the expectation. You can do whatever you want because they're the same thing. All right. The other thing is when you add two random variables together, then it's the same thing as if you first add them and then calculate the expectation, or if you calculate the expectation for each individually and then add them together. So this is really useful, in big part because actually, I'm sorry, this isn't a definition. Call this a lemma. So I'd be using the word lemma. It's like the word theorem, but a theorem is kind of a big thing. This is a smaller thing, so I'm calling it a lemma. And it's not a definition. I shouldn't have written that it was a definition, because a definition, it can be whatever you want. A lemma, this means that from the rules, you can derive that these two equations are true. You can prove that they're true given the rules of probability and of random variables. So it's a property of random variables. And one very cool thing is that, note, this is always true, no matter the relationship between x and y. Even if they are dependent. This is super nice. Independence is something that just makes all the math easy. When things are independent, math is easy to do. When you have events that are dependent, things get so complicated. Because this thing affects that thing, and then that thing might affect another thing, and it just becomes this big mess. I'm not sure if you guys are aware of the three-body problem, but it's a problem in physics. Let's say you have two planets, and one is orbiting the other. You can calculate for any position. So each of these have some xy position, and for some velocity, you can calculate what will happen. You can predict where each of these will end up after 1 second, 100 million years. You can calculate this, and it's a very straightforward, easy calculation. And it's easy because this has gravity, and this is pulling on that, and this has gravity, and this is pulling on that. But that's it. That's as much as they interact with each other. But when you add in a third body, this is called the three-body problem, which is an excellent Chinese sci-fi book, by the way. If you haven't read it, I highly recommend it. Very good. Anyway, if you have three bodies, you can't solve it, or we have no idea how to in in the world. 2 bodies, easy. Super, super easy. 3 bodies, no way. There's absolutely no way to calculate this. And it's because this has a gravitational pull on that. And so when 3 pulls on 1, then that will affect 1. But 1 is also pulling on 2. And 3 is also pulling on 2. So if you want to figure out how 2 moves, you have to calculate how much V3 is pulling on it, but then you also have to count how much it's being pulled on by V1 because of V3's influence on V1, and it just becomes a horrible mess. I mean, it's already getting messy, and I haven't even really delved into it. So that is an example of dependence, when one body pulls on another, and then that pulls on another, and then they're all interacting, and everything is dependent, and it's a nightmare. It's a big mess. But with expectation, everything is easy. These things are true, even if X and Y are dependent on each other. So when you're trying to analyze things, trying to figure out individually, like the probabilities of both of the things occurring at the same time, or one occurring and another not occurring, or how they depend on each other, it's a mess. But you talk about their averages, super simple. Just, you can take these 2 things and just consider them individually, all by themselves. And then you add them together and you're done. You know how the averages play with each other, even if it's very, very difficult to talk about the specifics of what they do. You can talk about what they do on average very easily. All right, so this is the reason why, or part of the reason why, expectation is such a big deal, because, and why it's foundational to so many different things, because it's really easy to work with, it simplifies things, and when you start talking about averages, and especially averages of averages, lots of things just sort of smooth out and become very reliable and clear. Okay, I think I've said enough about the linearity of expectation. I will give, well, I want to give another break, let's say 10 minutes. And after that, I'll choose 2 students to give an example of one gives an example for this, something we can calculate, and the other gives an example for this that we can calculate. But we'll do that after the break. So let's come back at 5:10. Okay. So hope you guys had a good break. Let's continue. There's only 1 or 2 other things I want to cover before the end of class. So yeah, next class I'm going to be talking about different types of random variables, Bernoulli and things like this. It'll get a little bit more into combinatorics, the combinations of things, and stuff like this, concentrations and stuff. So I don't want to get into any of that today. I just want it to be focused on the basics of random variables. So before our break, we were talking about the fact that expectation has this property called the linearity of expectation. And all that means is that both these two things are true for any variables x and y. But I wanted to just to make the point, I guess, go over some very, very simple examples. So I thought I'll pick out on some of you guys. Olga, are you there? Do you have a mic? Okay, how about Vincent?
Yeah.
Hey. Yeah, so what's an example random variable? It can be one that we talked about before or another simple one that you can come up with.
It would just be taking something like one of the colored sides of the die and then assigning it a number.
Okay, sure. Whatever, green. What numbers do you want to assign?
You can do 1 through 6.
1 through 6. Okay. So let's see. All right. So if this is x, well, I should really put it this way. Oh, well, yeah. It's fine. It's fine. I'll just keep it like that. Okay. Now I want to come up with. We're going to scale this by some number. So each of the numbers, we're going to make them proportionally bigger or smaller. We're just going to scale them. So what scale factor do you like?
I guess by 10.
10. Okay. So I'll call this x10 of red is equal to 10 x red. Which equals 10. Oh. Okay, so what should these equal? You say the first one's equal to 10? What's the second one?
It would be then 20, 30, up to 60.
Great. Okay. So what I want to do is to calculate the probability of, the expectation of x on the left, and on the right, we're going to compute the expectation of x sub 10. Okay. What is the expectation of x?
That'd be 3.5.
3.5. And where does that come from? The 3.5?
It's the average of all the numbers, like 1 to 6.
Yeah. Okay, and how about on the right?
It'd be 35.
35. Okay, and where does that come from?
This comes from the same place as it does on the left.
Okay. Okay. So we calculate it using the definition of expectation here. I'll put here by definition. So that's by definition of expectation that we have this. Is it true
I don't know that one.
that E of 10x, actually, you know what, I don't need these. Yeah, we're just multiplying it by the scalar. Okay, is this true?
I'm not 100% sure. I want to say no because I think like they're doing different things, but you get the same answer.
Well, this on the left, we've already calculated that to be 35. And this is 10 times 3.5, which equals 35. So you do get the same answer. Okay, let me convince you that this will always be true. This isn't an accident. This is true because it has to be true. If yeah, fine. I'll go back to this sort of pictorial way of looking at it. Here, the expectation is where the amount of mass is equal on the left and the right-hand sides. Agreed?
Yeah.
All right. So here that's 3.5. All right. Now, what happens if I do 10x? That's just adding zeros here. So then that would move this decimal point. Right? The amount of mass doesn't matter. All right? The amount of mass isn't changing. The only thing that's changing is the amount that I'm scaling all of the numbers. But the amount that I'm scaling all of the numbers is going to scale this number the same way. So here it's multiply this by 10, multiply that by 10, multiply that by 10, by 10, by 10, by 10. And so you can multiply every point along here by 10. That's sort of what you're doing when you multiply this by 10. Or what happens if you divide by, let's say, 2? So now this is a half. That's 1, that's 3 halves, that's 4 halves, that's 5 halves, that's 6 halves. Does the position of the expected value change at all?
No.
No. But this number should also be scaled with everything else, because calculating what this number is, I mean, it's the middle number between this one and this one. So this is the same as 4 minus 3 over... sorry, that's not right. Yeah, I won't say that. Yeah, so this is why it's scale invariant, and it will always be that way. Does this help a little bit as far as convincing you that no matter how you scale, the expectation will scale in the same way?
Yeah, it makes a lot of sense.
Okay, great. All right. Well, thank you, Vincent. How about, I don't know, Andrew? Do you have a mic? You don't. Okay. Hey. All right. Well, just because I want to give an example of this. Actually, let me copy both of these. I wonder where those flipped. Okay. So now I just want to do some concrete example, like we just did, to show that this is also true. Andrew, are there random variables that you like for x and y? Two and three. So they have to be random variables. Random variables are not numbers. They can be numbers with a certain probability. Yeah, so, I mean, x. So what is x? Let's say, here, I'll give you a starting point. Let's say that x and y are both games, and the outcomes of these games are how much money you earn. So if you play game X, what's an amount of, what are the different payouts for game X? Let's say that X is flipping a coin, and if you get heads, you get a certain amount of money. If you get tails, you get a certain amount of money, or you lose a certain amount of money. So if I flip a coin and I get heads, how much money do you want me to win or lose? 50. Okay? So the probability of x equals heads. Oh, sorry. Is a half. And the probability that x equals tails. Oh, 50 each. Well, that's an easy game. You just always get $50. Okay. Fine. So this is x is payout flipping a coin. And I'll say y is payout for spinning a color wheel. So let's say with 3 colors. Trying to keep this small. Red, green, blue. Red, green, blue. So there's some color wheel. Or maybe this is the color wheel, whatever. But you spin it, and if you land the pin on that color, you either pay money or you earn money. So let's say I spin and it lands on red. What should the payout be for that? Yeah, if you land on red. Okay, so you're saying the probability of red is 2/3. How much does it pay? $50. Okay, how about the other colors? And the other third is 0, but there are 3 different colors. Okay, sure, that's fine. So I'll make these $50, green, and the other pays out nothing. Oh, so red is 1/3. And half of the money. Okay. So should each of these be 1/3? Correct. Okay. Great. So I don't want to mess this up too much. Too much. All right. Then what's the expectation of x? What's the expected payout for flipping a coin when either side pays out $50? No, this is for x. X is about the coin. 2/3 will get me $50. 2/3 of what? Yeah, right. So 100%, you're getting $50 because if it lands heads, you get $50. If it lands tails, you get $50. You can also say that this is 50 times a half plus 50 times a half, which is 50. Okay. E of y is what? So E of y, now this is the color wheel. Two-thirds gets me $50. Not quite right. Red and green will give you $50, yeah? So you have a 2/3 chance of getting $50. You have a 1/3 chance of getting $0. But the expectation is, what if you played this game 100 times? Then on average, how much money would you get? So you could get red with a probability of 1/3, or you could get a green with a probability of 1/3, or you could get a payout of 0 with a probability of 1/3. So this is 100 over 3, which is, 33.3 repeating. Yeah, so the expected value doesn't need to be one of the outcomes. Yeah. In this case, you play it, you play this game over and over and over and over and over. A lot of times you win $50, sometimes you win nothing, but on average, you could expect to earn 33-ish dollars over when you're summing up over many things. Okay? All right. Now, there's the expectation of x plus y. So now, this is you play both games. You flip the coin, you get a payout or not, and then you spin the color wheel. So, in each time, you play both games. Yep. E of x equals 50. E of y equals 33.3, yeah? You want to say 83.3, but that doesn't seem right. Well, it's exactly right. This does, in fact, equal 83.3. That's correct. But there's two ways of calculating it. There's the easy way, which is what I'm trying to show through a concrete example. That E of x, that you can calculate it easily this way. But let's say we're not sure if this is true or not. Then, taking this, you could get heads red, heads, tails red. Heads green, tails green. Or heads blue, tails blue. These are all of if you're playing this game one right after the other, these are the different outcomes. The payout for these, well, this would be $50 from the coin plus $50 from the red, with a probability of 1/2 of getting the heads and a probability 1/3 of getting the red. Plus, if you get tails, that's a $50 payout, plus another $50 payout, times this. Heads green, $50 plus $50. You have a 1/2 chance of getting heads. You have a 1/3 chance of landing on green. Tails pays out 50. Landing on green pays out 50. You have a 1/2 probability of flipping tails. You have a 1/3 probability of getting green. And for heads blue, each of these pay out just $50 because blue pays nothing. Okay, so if we do this, this is 100 over 6, 100 over 6, 100 over 6, 100 over 6, 50 over 6, 50 over 6. Which is 500 over 6, which is 83.3. So there, I just proved it. This is the taking the long way. This is using the definition of expectation. And this is now a property of expectation. So you don't have to go through this. That's the nice thing about the linearity of expectation. You don't have to write all this crap down here at the bottom. You can skip all of it, and you can just say it equals the expectation of x plus the expectation of y, and you're done. You could go the long way. You'll certainly get the same answer, but you don't have to. And so that's one reason why, linearity of expectation is great to know. It's so useful. It saves a ton of time. Okay, so that is it for today's class. Again, the homework's out. It'll be due next Tuesday. Next Tuesday, I will kind of blow past this expectation things, although you should now know enough to do your homework. There's a couple of ways that you can solve that expectation problem. And I think you know enough now to be able to do it. And next Tuesday, it'll be different stuff that we talk about. So thank you, everybody, and have a good weekend.